Hello, 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 and welcome to Math. Happy Monday. We're ready to get back at it and marching towards the end of the year. I didn't even plan to do that when I started the stream, but it needed to be done. You're welcome. Okay, dividing fractions part 3. We've been kind of digging in a lot on the conceptual nature of dividing fractions. What does it mean to divide a fraction? Okay, and we spent a little time working on it last week, 2 parts working on it last week, and really focusing on sort of using division and multiplication as inverse operations and thinking about them in different ways. We're going to put that all together today and kind of look at a really efficient way, some would call it a shortcut, a really efficient way to solve for an unknown when you're dividing fractions. That's what you're going to need, something to write on, something to write with, and down there are the I cans. I'm going to read them out for you. I can define inverse operation. I can write a multiplication equation that is the inverse of a given division equation, and I can use inverse operations to solve for an unknown in a fractions division equation. And as always, for those of you in my class, the Google Hangouts chat thread is open. For those of you that aren't in my class, just as a kind of a disclaimer, we are having trouble getting all of my students logged into the chat so they could ask questions in real time. So we have our own separate chat thread going for live questions. And so that's why the chat is now closed for our live streams. But, you know, if you have questions, ask your classroom teacher, because I bet they could help you. All right, let's get to the meat of our lesson today. Dividing and multiplying, again, best friends forever. They're inverse operations. You know, if division does something and we're like, oh, I kind of want to undo that, multiplication can clean up the mess, and vice versa. Let's look at actually multiplication of fractions here and remind ourselves of one way that we use inverse operations to solve fractions unknowns. We already learned this with multiplication of fractions. We had 4 times 1/3 equals n, or equals our variable, right? And we thought about this as 4 groups of 1/3, right? Or 4 divided by 3 equals n, right? Essentially thinking about when we multiply fractions, we multiply the numerators and we multiply the denominators. In this case, 4's denominator, because it's a whole number, is 1, right? So we're doing 4 times 1 to get our numerator, 1 times 3 to get our denominator, which is 4/3, or similarly 4 divided by 3, right? Fractions, division in disguise, okay? Now, one thing I'm looking at with this is essentially what we're doing, particularly when the numerator is a 1. This is when kind of things become clear, right? We're essentially doing, oh, well, I'm just, rather than multiplying by 1/3, I'm almost dividing by the denominator. I'm saying 4 divided by 3 wholes is the same as 4 times 1/3. So essentially all we're doing here is we're switching the positionality of the numerator and the denominator, and we're switching to the inverse operation. I wonder if that works the other way. I wonder if that works the other way with 4 divided by 1/3 equals n. Does that equal 4 times 3/1, or 4 times 3 wholes? Well, let's think about this. Go back to our conceptual here. If we're thinking about 4 divided by 1/3, we're considering, okay, 4 is 1/3 of a group. We've taken 4, we've put it into 1/3 of a group. So I'm going to draw some thirds here. We've taken 4, we've put it into 1/3 of a group. And our group in this case is n. right? And we want to know what the whole group equals. Well, if this third equals 4, stands to reason all the other thirds equal 4, right? Otherwise, they're not equal thirds. 4 plus 4 plus 4 is 12, or 4 times 3. Oh. So what we can do if we have a fraction and we're dividing by that fraction, we can just take that fraction and flip the numerator to the denominator and the denominator to the numerator. And we end up with a multiplication equation that matches it. Interesting. I wonder if that works all the time or if this was just a fluke. Let's try one more and find out. Or let's look at, actually, let's go a step further. Let's look at the one I already have on the board from last week. 5 divided by 1/5 equals n. Okay? Again, this is the equal number of equal groups. So this is 1/5 of a group. We're taking our 5, we're putting it into 1/5 of a group. How much is one group? In this case, does that look like 5 times 5? You bet it does. 5 times 5 wholes, or 5 over 1, equals 25. Just like 5 divided by 1/5 equals 25. So there's our really efficient way of finding the unknown in a fractions division equation. Is you take the divisor and you switch the numerator and the denominator. You flip the numerator and the denominator for each other. And then you multiply down here. 5 times 5 over 1, or just 5 times 5, equals 25. Now, let's go to the digital whiteboard, and I'll give you a couple. And then I want to look at a different case. Does it still work when the numerator is not a 1? So here we have our whiteboard, and let's try this one. Let's go with 8 divided by 1/6 equals what? If you get done with that quickly, try 10 divided by 1/9. Okay. Try those quickly. I'm seeing we're caught up in the chat. Yes, n does equal 25 in that last case. What about these ones? 8 divided by 1/6. If 8 is 1/6 of a group, how much is the whole thing? 10 divided by 1/9. If 10 is 1/9 of a group, how much is the whole thing? Stalling for time here because I do know and realize that my class chat is a little bit behind the live video. So we'll give it a little bit more time here. But remember, what we're going to try doing is we're going to try and flip the divisor. Okay, so take that 1/6 and trade places with the numerator and the denominator and see what you come up with. And then remember to change our division to multiplication as well. So for the first one, we're going to change this to multiplication. And then we're going to switch the 1 and the 6. We're going to put the 6 on top and the 1 on the bottom. And since it's a whole number, since there's 1 in the denominator, we don't actually need the denominator. So we can just say 8 times 6. And however you do 8 times 6, works for me. Maybe it's 8 times 3 twice, because you know 24 is 8 times 3. 24 plus 24, 48. Or maybe you just have it automatic that 8 times 6 is 48. Maybe you know 8 times 5 is 40, and you have to add another 8. That's another way to get to 48. Lots of different ways to get to 48. Now let's take the second one here. 10 divided by 1/9. ninth. Okay, same thing here. Our division, we're going to use the inverse operation, which is multiplication, and then we're going to flip the fraction. So now it becomes 10 times 9 over 1, or just 10 times 9. And that is same thing as 1 times 9 times 10, which is 90. Now, does this work? Does this work when the numerator is not 1? What does that look like when the numerator is not 1? Maybe we have something like, and I'm going to do that. I'm going to go to pink. Maybe we have something like, oh, I don't know, 12 divided by 2/3 equals n. Now, before we do that, we want to draw ourselves a model here. So we're saying 12 is 2/3 of a group. And we want to know what the whole thing is. So I'm going to draw out my thirds. Now 12 is 2/3 of the group. So this bit equals 12. We want to know what the whole thing is. If 2/3 equals 12, how are we going to know what 1/3 equals? Well, if we zoom in here and take a look at our 12, it's in how many equal pieces? Well, not equal by the way I drew it, but equal in math form. It's in 2 equal pieces. So we can think about what's 1/2 of 2. Or what is 12 divided by 2? 2 times what equals 12? Right? So in this case, we would get 6. 6 plus 6 equals 12. Would you agree? Yeah. So this third must also equal 6. So that means, what is the value of the whole thing? What's the value of our n? It would be 18. Okay, so that's how we've kind of proved it with a model. Now let's see if our shortcut, if our flip the divisor and multiply shortcut works here. Okay, so what is the equation going to look like if we're flipping the divisor and multiplying? Instead of, I'm going to zoom out, scoot it to the side a little bit. Instead of 12 divided by 2/3, we have 12 times what? Flip the position of the numerator and the denominator. So put the 3 on top and the 2 on the bottom. And we end up with 12 times 3/2 equals n. Okay, now let's try that. I'm going to put a 1 in the denominator of my 12, just so I remember that I'm not multiplying by 12/12ths, I'm multiplying by 12 wholes. Okay, then we multiply straight across. 12 times 3 goes on top, and 1 times 2 goes on the bottom. So let's do 1 times 2 first, it's smaller. So we're going to be in halves. And then how many halves? 12 times 3, or 12 plus 12 plus 12, or 24 plus 12, or 10 times 3 plus 2 times 3. All roads lead to 36 halves. 36 halves. Okay, so if 36 is the whole thing, and we're cutting it in 2 halves, dividing it by 2, what is it going to be, right? Yeah, it's 18. 18 plus 18 equals 36. So our 36 halves, because we can, essentially what we're doing here is we're dividing by 2 over 2. 36 divided by 2 is 18. 2 divided by 2 is 1. And we end up with 18 over 1, or 18. So we get that same answer we get that same answer that we got when we used our shortcut, or when we drew our model, I should say. Okay? So the name of the game here, when you get to your exit ticket, because you will see some that do not have, or the numerator is more than 1. Remember, flip the divisor, then multiply. Flip the divisor and then multiply. And if you do that, you should end up with an accurate answer. And if you want to check, and it is actually pretty fun and interesting to kind of do this extra work of modeling, right? 12 divided by 2/3 is 18. So thinking about, okay, if 12 is 2/3 of the whole thing, what's the whole thing? So I'm going to draw out some thirds. 12 equals 2 of them. So what does 1 of them equal, right? That particular modeling and visualization is really important, okay? That helps get more flexible with our mathematical thinking. So we're going to continue to practice this stuff even though we know the shortcut, because solving for n, or solving for x, or solving for the unknown, that isn't always what math questions or math situations ask you to do. Sometimes it asks you to draw a model. So we've got to be prepared to draw a model, right? If we want to be architects or engineers, right? Drawing a model and drawing mathematically accurate models is crucial. Otherwise, we're going to end up at a fence that's not long enough, or too long, or too tall, or a building that doesn't stand upright, okay? So, you know, the real life applications of this stuff don't just involve using the shortcut and solving for n, right? It's also important to be drawing these models. And we're going to keep doing that as we go. But now with the shortcut, today is really just a day to practice that shortcut, practice that efficient method, and solve for n on the exit ticket. Thank you all for tuning in. We will be back tomorrow with part 4, when we start thinking about fractions divided by fractions. Enjoy. Good luck. Have a great rest of the day. I'll see you soon.